Okay, so today we are going to read Chapter 6, Section 2 and take Cornell notes. So the first thing that we need to do is to title our page. This is going to be on page 117 in your student journal, and our title is going to be over here on the side is going to be 6.2 Cornell notes, and whatever today's date is, which we're going to put October the 30th, 2015. All right. The next thing that we want to do is to set up our Cornell note page. So let's get a piece of paper and draw our line. Since we take modified Cornell notes, we're not going to do a summary. We're just going to bring this line all the way down. And you can see it doesn't really matter if it's straight. Then we're going to put a line at the top. And Chapter 6, Section 2 is called Electrons and Chemical Bonds. So that's going to be the title of this page. Electrons and Chemical Bonds. Okay, so let's start reading. I always like to start my reading with looking at the teak, which tells us what we're supposed to be learning in this chapter. It's over here on the side and it's in green. This teak reads, recognize that chemical formulas are used to identify substances and determine the number of atoms of each element in a chemical formula containing subscripts. So by the end of this, we should know something about chemical formulas, what substances are in them, the number of atoms, and what a subscript is, we hope. All right, so let's start our reading, and I'm going to read a paragraph, and then we're going to take notes if we think we need to. So, the discovery of energy levels in an atom solved a 2,000-year-old mystery. The mystery was why elements combined with other elements only in a particular ratio or not at all. For example, why do two hydrogen atoms bond with one oxygen atom to make water? Why isn't there a molecule with 3 hydrogen atoms and 1 oxygen atom? The answer has to do with energy levels and electrons. Okay. Is there anything there we need to take a note about? I don't think so. I think we've covered valence electrons quite a bit in class, and I don't think we really have anything to write about there. So I'm going to read the rest of this page and see if there's anything on this page that I think is noteworthy. Valence electrons. What are valence electrons? Now you see over here on the side, it gives us our key words if we're going to be taking notes. So, what are key valence electrons? This paragraph is going to answer that. Valence electrons are electrons in the highest energy level of an atom. These electrons participate in the formation of chemical bonds. You can think of valence electrons as the outer skin of an atom. Electrons in the inner energy levels do not see other atoms because they are shielded by valence electrons. For example, chlorine has 17 electrons total, with 7 valence electrons. The first 10 of chlorine's 17 electrons are in the inner energy levels. Figure 6.9. Let's look at figure 6.9, and you can see that it has chlorine and sodium, 17 total electrons, 7 valence electrons. So it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 electrons, 7 valence electrons, which means it has 7 electrons in the outer ring, or outer energy level, which we have 1, 2, 3, 4, 5, 6, 7. So you know from class that that means that this atom wants to find an electron somewhere because it only needs 1. All right, and let's look at sodium. Sodium's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons. So you know from class that sodium wants to lose 1 electron because then it'll get rid of this basically this outer shell here, and it'll just have 8, our magic number here, so it will be fulfilled or full. So typically sodium will say, hey, chlorine, you need an electron. I don't want it. You can have it. And so it would give chlorine its electron, which means that chlorine at that point has become negatively charged because there are more electrons than protons. And it would mean that sodium has become positively charged because there will be more protons than electrons. Thus, chlorine and sodium will be attracted to each other because one is positively charged, one is negatively charged. And we know that positive and negatives attract. Do we need to take any notes about this? Oh, yeah. Okay, we're back. So I made a mess and I've cleaned it up. At this point, we're going to start taking some Cornell notes. And I think our key word should be valence electrons. So I'm going to write valence electrons as our key word. And it said here that the valence electrons, even in the vocabulary here, it says an electron in the highest unfulfilled energy level of an atom. These electrons participate in the formation of chemical bonds. So, what we're going to write here is really what we already know about valence electrons. We know that they are the electrons in the outer shell. I'm going to write energy level down because it's actually more accurate. They're not shells. They're not hard things, and they don't make the electron stay in a specific area. So we're going to use the word energy shell. Anything else there that we should write? I don't think so. So we're going to keep reading about it. And, we might want to write down that the electrons in the inner energy levels are filled. So let's write that down. Okay. Electrons in the inner energy level are full. Not valence electrons. And as you can see from my handwriting, there is a reason why I typically type my notes. Okay, so let's keep reading. I'm going to move my notebook over and find my guide paper. And here we go. It says over here, most elements bond to reach 8 valence electrons. Let's find out why. It turns out that 8 is a magic number for chemical bonding. All elements are heavier than boron, elements with the atomic number higher than 5, form chemical bonds to try to get to a configuration with 8 valence electrons. 8 is a preferred number because 8 electrons are complete energy-filled levels. The noble gases already have the magic number 8 valence electrons. They don't form chemical bonds because they don't need to. Okay, so I'm going to write down that 8 is a magic number. 8 is a magic number. And you guys know that I like to abbreviate, so I'm going to use the pound sign or hashtag as you guys call it because that also means number. Okay, 8 is a magic number. This will help me remember that my atoms are trying to get to that magic number of 8. Okay, that's all I think we need to take for here. So let's go to the next section. Lighter elements bond to reach 2 valence electrons, and hydrogen is special. For elements with an atomic number of 5, boron or less, the magic number is 2 instead of 8. For these light elements, 2 valence electrons completely fill the first energy level. The elements hydrogen, helium, lithium, and beryllium and boron form bonds to reach the magic number of 2 valence electrons. Okay, do we need to take a note there? I don't know. What do you think? Yeah, I think we will. So let's write down. It's kind of hard to record this with the book, but let me move the book over. That's better. Okay. So I'm going to write hydrogen, helium, lithium, beryllium, and boron want 2 valence electrons, while all other elements want 8. And I'm going to refer back to 8 as a magic number. Okay, y'all got that? All right, let's read about hydrogen. Hydrogen is special because of its single electron. Hydrogen can also have 0 valence electrons. 0 is a magic number for hydrogen as well as 2. This flexibility makes hydrogen a very sticky element. Hydrogen can bond with almost any other element. Okay? Remember that carbon is a special element because it wants to bond with everything. Hydrogen is a special element also because it can combine with anything it wants to. Okay. Does that require a note? I don't know. I think we're going to make one just so we remember. I'm going to make a keyword hydrogen. I'm going to say can bond with anything, can lose, share, or steal 1 electron to be happy. Okay? Remember that when you're taking notes, it doesn't matter if your English is grammatically correct. These notes are for you to study. All right. I think we're doing good. I'm going to flip the page, and so should you. So you're now on page 158 in your textbook. And let's read on. All right. Valence electrons and the periodic table. Second period of elements. I'm going to read this whole page because I think we might be ready, or maybe a half page. Let's see how far we get. The illustration below shows how electrons in the elements in the second period, lithium and neon, fill their energy levels. 2 of lithium's 3 electrons go in the first energy level. Lithium has 1 valence electron because its third electron is the only one in the second energy level. That's a whole lot of words without knowing what they mean. So let's look down here at lithium. All right, and it says that 2 of lithium's 3 electrons go in the first energy level. We knew that, right? We knew that the first one's got 2. And lithium has 1 valence electron because its third electron is the only one in the second energy level. We knew that also because we've been building atoms already, so we're pros at this. Okay, and we know that if it's got 1 valence electron and it needs 7 more to become full, it is so much easier for it to lose this electron, give it away to somebody, than it is for it to go out and find 7 more. So it's going to lose its electron. It's also saying that beryllium likes to do that as well, because beryllium needs 1, 2, 3, 4, 5, 6 more to fill its shell. So it's easier to lose 3 than to go out and find 6. All right. I think that's as far as it got. So let's keep reading. Going from left to right across a period, each successive element has 1 more valence electron. Now we know that also because we know that in group 1 it's got 1 valence electron, and group 2 has 2 valence electrons, and group 13 has 3, group 14 4, and so on and so forth. So we know that. Beryllium has 2 valence electrons, boron has 3, and carbon has 4. Each element in the second period adds 1 more electron until all 8 spots in the second energy level are full at an atomic number of 10, which is neon, a noble gas. Neon has 8 valence electrons. So this is just showing us period 1. We have 1 valence electron, 2, 3, 4, 5, 6, 7, and 8 valence electrons. Do we need to take any notes there? Gosh, I don't think so. I think we already have this. We know it. If any of this confuses you, then maybe you might want to pause it here and take some notes on your own. But this is what we've been studying for the last couple of weeks, so I think this is just a reminder of what you already know. So let's move on to bonding. All right. I dropped my mouse, so I'm going to pick it up real quick. All right, bonding. And you guys know that I'm a big proponent of using your smart fingers, so I'm going to use my pen. All right. Oxygen has 6 valence electrons. To get to the magic number of 8, oxygen needs to add 2 electrons. Oxygen forms chemical bonds that provide these 2 extra electrons. For example, a single oxygen atom combines with 2 hydrogen atoms because each hydrogen can supply only 1 electron. Oxygen combines with 1 beryllium atom because beryllium can supply 2 valence electrons. To give oxygen its preferred number of 8, see figure 610. Okay, so figure 610 here shows you that hydrogen, there's 2 of them, and that's what this little number here means. Remember, that's a subscript. So we've got 2 hydrogens and 1 oxygen. And you know that oxygen has 6 valence electrons. And you know that hydrogen has 1. So hydrogen needs 1. So oxygen is going to share 1 with hydrogen, and hydrogen is going to share 1 with oxygen. Oxygen is going to share 1 with this hydrogen, and this hydrogen is going to share 1 with oxygen. So now hydrogen has 2, and oxygen has 8. Right? And we're going to learn how to do this when we get on to the end of the chapter with the Lewis dot structures. So let's keep reading. Double bonds share 2 electrons. Carbon has 4 valence electrons. Oh, you can't see, can you? All right. Hopefully you're reading along in your book. Carbon has 4 valence electrons. That means 2 oxygen atoms can bond with a single carbon atom, with each oxygen atom sharing 2 of its carbon atom's 4 valence electrons. The bond in carbon dioxide are double bonds because each bond involves sharing 2 electrons. Okay? So they're actually saying that here hydrogen sharing an electron and hydrogen sharing an electron are giving it up. Oxygen's using it because it only has 1 bond. All right. I don't think it gives us a... Yes, let's see figure 611. So figure 611 shows that carbon needs 8. It already has 6. So oxygen shares 2 and carbon shares 2. So now oxygen, this oxygen has 8, this oxygen has 8, and this carbon now has 8 as well. And if you don't understand this, don't stress out, because when we go towards the end of the chapter with this Lewis dot diagrams, I'll try to make it a little more understandable. Okay? So, do we need to take any notes there? Well, let me see. Is there anything here that we need to take a note about? No, I don't think so. I think you know everything you need to know about this so far. So we're going to continue our page on 159 reading Lewis dot diagrams. Dot diagrams of the elements. A Lewis dot diagram shows a chemical symbol surrounded by 1 to 8 dots representing the valence electrons. Each dot represents 1 electron. Lithium has 1 dot, beryllium has 2, boron 3, etc. Figure 6.12 shows the dot diagram for the first 10 elements. Well, you guys are already familiar with this because we've already done this on one of our periodic tables. So let's just look at it. Neon, 1, 2, 3, 4, 5, 6, 7, 8. Fluorine has 7. Oxygen has 1, 2, 3, 4, 5, 6. Nitrogen, 1, 2, 3, 4, 5. Carbon, 1, 2, 3, 4. Boron, 1, 2, 3. Beryllium, 2. Lithium, 1. And hydrogen, 1 also. Let's continue reading. Dot diagrams of molecules. Each element forms bonds to reach one of the magic numbers of valence electrons, 2 or 8. In dot diagrams of a complete molecule, each chemical symbol has either 2 or 8 dots around it. if you remember, it starts off with 1, 2, 3, 4, 5. So we've got 1, 2, 3, 4, and 5. Hydrogen only has 1, so hydrogen shares 1 here, here, and here. Now hydrogen has 2, hydrogen has 2, hydrogen has 2, nitrogen has 1, 2, 3, 4, 5, 6, 7, and 8. Let's look at carbon, methane. Again, we know carbon has 1, 2, 3, 4. So if I were to draw this for you, it would look like this. Carbon, 1, 2, 3, and 4. And we know that hydrogen has 1. And since it says C, we have 1 carbon, H4, which means we have 4 hydrogens. So we're going to put a H, 2, 3. There are 4 hydrogens, and each one has 1 valence electron. So now hydrogen will have a full shell with 2 on each, and carbon won't, because now it has 8. 1, 2, 3, 4, 5, 6, 7, 8. Wonderful. Carbon tetrachloride. Carbon, we'll do this together too. Carbon has 1, 2, 3, 4. And over here it says that chlorine, chlorine is not on our list. So let's look on the periodic table of elements and find out where chlorine is. Chlorine is in period 3, group 17, and since it's in group 17, we know that it has 7 valence electrons. Okay, and it says CCl4, so we know we have 4 chlorines. Let's just go ahead and put our chlorines down so it'll make it easier. And let's do our shells. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, and 7. 1, 2, 3, 4, 5, 6, and 7. Now everybody's happy. Chlorine's got 1, 2, 3, 4, 5, 6, 7, 8. And all of them look like that. And then carbon has 1, 2, 3, 4, 5, 6, 7, 8. Everybody's got the magic number of 8, so everybody's going to be happy. Alright, examples of dot diagrams. Carbon has 4 dots and hydrogen has 1. One carbon atom bonds with 4 hydrogen atoms because this allows the carbon atom to have 8 valence electrons, 8 dots, 4 of its own and 4 shared with a hydrogen atom. The picture above shows dot diagrams for carbon dioxide, ammonia, methane, and carbon tetrachloride, a flammable solvent. Okay, so we have something to do here. But before we start doing this, I think it's time for notes. Move my book out of the way, and I'm going to make my keyword. What do you think it should be? Yeah, I think it should be Lewis dot diagrams. Alright, what did we learn about what a Lewis dot diagram is? Well, I think the basis of what it's telling us is that it's a diagram that shows a chemical symbol being the C for carbon, the Cl for chlorine. You know what chemical symbols are. Okay, diagram that shows a chemical symbol surrounded by 1, 2, 8 dots that represent valence electrons. Ta-da! Alright, I think that's all we got from this page. So let's go ahead and work out the problem at the bottom of the page. Now, I will always want you to work out the problems because they will show you if you know what you're doing or not. So let's work out this problem and see if we know. I am going to work it out, but I want you to stop the tape or the recording, and I want you to work it out yourself. Okay? So go ahead and stop it and work this out, and then hit the go button, and we'll work it out together. Right? Dot diagram for water, H2O. Given the chemical formula H2O, we know that we've got to have 2 H's and 1 O. Alright? H2, this 2 being the subscript, which tells you how many atoms you have of H. Okay, hydrogen has one valence electron, and oxygen has how many? I don't know. 6. 1, 2, 3, 4, 5, 6. Let's try to make some kind of a solution to this, which they've done it in the book for us, but we're going to do it anyway. We have O with 1, 2, 3, 4, 5, and 6. And we have hydrogen with 1 and 2. We are off. Okay, let's try the one that says return. Draw the diagram of beryllium oxide, which is BeO. So our symbols will be Be and O. And beryllium has 2 valence electrons, and oxygen has 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. So I would put 1, 2, 3, 4, 5, and 6 like this because beryllium has 2 that it's going to share. Oxygens and 1 carbon. Page 116 in the textbook. Let's start off with the vocabulary word, oxidation number. Indicates the charge of an atom when an electron is lost, gained, or shared in the chemical bond. An oxidation number of +1 means an electron is lost, and -1 means an electron is gained. Okay, you guys know that because we talked about it on Friday. So, let's start our reading. Oxidation numbers. What is an oxidation number? I wonder. A sodium atom always ionizes to become sodium plus, a charge of +1, when it combines with other atoms to make a compound. Therefore, we say sodium has an oxidation number of 1+. An oxidation number indicates the charge of the remaining atom, ion, when electrons are lost, gained, or shared in a chemical bond. Figure 6.13 shows the oxidation number for some elements. Notice that the convention for writing oxidation numbers is the opposite of the convention for writing the charge. When writing the oxidation number, the positive or negative symbol is written after the number and not before it. Now, if you remember from Friday or from your reading, let me see if I can find the page. When it was talking about ions, here, page 154, it showed magnesium 2+. But over here, it's going to be magnesium 2+. Okay, over here, it shows magnesium 2+. Alright, so when we're talking about the oxidation number, it's the number and then the plus sign, not the plus sign and then the number. The plus sign and then the number tells you what charge it has. Okay, but when you write it, it's the number plus then the plus sign. I hope I didn't confuse you too much. Oxidation numbers in the periodic table. Oxidation numbers correspond closely to the elements group on the periodic table. All of the alkali metals, you know that's group 1. All of the alkali metals have an oxidation of 1+, since these elements all prefer to lose 1 electron in its chemical bond. All the halogens have an oxidation number of 1-. You know, halogens are your group 17. Because these elements prefer to gain an electron in chemical bonds. The diagram below shows the trend of oxidation numbers across the periodic table. Most transition metals have complicated oxidation numbers because they have many more electrons, and that's why we don't talk about these guys. Remember that. High school chemistry, you'll talk about these transition elements and all the ones underneath it. Okay, so do we need to take a note? I think so. Get our notebooks out. And our keyword is going to be oxidation number. Okay, so what do you remember? I remember that from the definition that it tells how many electrons are lost, gained, or shared when bonding 1's oxidation number is 1 plus because it wants to lose an electron. Okay? Sorry. Wants to lose one electron. I ran out of room, so I put a minus sign with a circle around it. You guys know that minus is negative, and which means it's an electron, and plus means it's positive, which means it's a proton. Alright, so I'll probably write down that group 17's oxidation number is going to be 1 minus, 3 minus, is 1 minus because it wants to gain 1 electron. Alright. I'm also going to put a side note that I didn't read, but you should absolutely know, is that when the elements combine, to make molecules, and ionic compounds, their total charge, I'm going to write electrical charge just so you know what I'm talking about. Their electrical charge is always 0. This is going to help you predict chemical formulas. Okay. Alright, let's look at this book again. Alright, so in the book it shows you the oxidation number. Group 1 is going to be 1 plus, group 2 is 2 plus, 13 is 3 plus, 14 is 4 plus, and then we start going back down. Okay, group 14. Group 15 is 3 minus, 16 is 2 minus, and 17 is 1 minus because group 15 is trying to find 3 electrons, which gives it a negative charge of 3. Group 16 is trying to find 2 electrons, which means it's going to have a charge of negative 2 or 2 negatives. And then group 17, or halogens, are trying to find only 1 electron, so once it finds them, it will become negatively charged by 1. Okay, I think you guys understand that. It also has a little chart over here to make it easier. And on our periodic table that we have in class, it also has those sticky notes at the top with the oxidation numbers. That's what's up there if you guys didn't know. So let's move on to page 161. Let's get this homework done. Predicting a chemical formula. Oxidation number is a compound add up to 0. Oxidation numbers in a compound add up to 0. Oh, I think I got ahead of myself. That's probably what it's going to tell me now. So let's go ahead and read this. When elements combine in molecules and ionic compounds, the total electrical charge is always 0. Dang, that's like verbatim of what we wrote. Alright. This is because any electron donated by one atom is accepted by another. The rule of 0 charge is easiest to apply using oxidation numbers. The total of all oxidation numbers for all atoms in a compound must equal 0. This is an important rule and allows you to predict many chemical compounds, or chemical formulas. We already took that note, so we don't have to take it now. That's awesome. Okay, the oxidation number for all atoms in a compound must add up to 0. Well, they put this in bold and a different color, so it must be really, really important. And we already wrote that down, so we're feeling pretty good. An example of carbon tetrachloride. To see how this works, consider the compound carbon tetrachloride, figure 614. Carbon has an oxidation number of 4 plus. Chlorine has an oxidation of 1 minus. It takes fluorochlorine atoms to cancel with the carbon's plus 4 oxidation number. Be careful not to read the oxidation number as typical math problems in the diagram. Although 4 plus is shown next to 1 minus, this does not mean 4 plus 1 equals 5. Predicting a chemical formula. Iron and oxygen combine to form a compound. Iron has an oxidation number of 3 plus. Oxygen has an oxidation of 2 minus. Predict the chemical formula of this compound. Okay, let's see if we can do this without looking at the book. Okay. Oxidation number Fe 3 plus, NO 2 minus. I'm thinking we're going to need to come up with something like 2 times 3, so let's see what it says. The oxidation for all numbers in the compound must add up to 0. Okay, so I think we're going to need 3 oxygen and 2 irons, but let's see what they say. 3 oxygen atoms contribute to the total oxidation of 6 minus. It takes only 2 iron atoms to get a total oxidation of 6 plus. Therefore, the chemical formula is FeO3. Dang, we're smart. F2O3. Just what we said. And that's using common sense and math. So, let's look at your turn. Dun, 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 and see what we get. Predict the chemical formula of the compound containing beryllium, Be, which has an oxidation of +2, and fluorine, F, which has an oxidation of 1 minus. Well, this one's pretty easy. If beryllium's got +2 and fluorine has 1 minus, then we need 2 fluorines because 1 minus and 1 minus is 2 minus. So our formula is going to be BeF2. Alright. We missed some stuff on the side here. Let's read this stuff. Multiple oxidation numbers. Many periodic tables list multiple oxidation numbers for most elements. Okay, now the one in the STAR test does not, and the one that we have on our board does not either, I don't think. We'll look at it later though. This is because more complex bonding than what we've discussed so far is possible. This course gives you the fundamental ideas, but there is a whole lot more to learn. When multiple oxidation numbers are shown, the most common one is usually in bold type. For example, nitrogen has a possible oxidation of 5 plus, 4 plus, 3 plus, 2 plus, or 3 minus, even though 3 minus is the most common. Okay, that's interesting. Alright, figure 6.14. The total of oxidation numbers for each atom in the molecule must be 0. So, carbon's +4, and we got -1, 2, 3, and 4 equals 0. Okay. Next page, we're almost done. Whether or not a compound is ionic or covalent bonds depends on how much an element needs an electron to get the magic number 2 or 8. Elements that are very close to the noble gases on the periodic table tend to give or take electrons rather than share them. These elements often form ionic bonds rather than covalent bonds. Remember, ionic means that you're giving it away and you become charged, and covalent means that you're sharing. Co means share. Sodium chloride is ionic. For example, sodium has 1 electron more than the noble gas neon. Okay, right here. Here's sodium. Here's neon. Where were we? This is why you should just read and not get caught up in each other. Okay. Sodium has a very strong tendency to give up an electron and become a positive ion. Chlorine has 1 electron less than the noble gas argon. Therefore, chlorine has a strong tendency to accept an electron and become a negative ion. Sodium chloride is an ionic compound because sodium has a strong tendency to give up an electron and chlorine has a tendency to accept an electron. Widely separated elements form ionic compounds. On the periodic table, strong electron donors are on the left, over here, and strong electron acceptors are on the right, over here. The further apart the two elements are on the periodic table, the more likely they are to form an ionic compound. So it means that if you've got one over here and you've got one over here, they're probably going to form an ionic compound. But if you've got one here and you've got one here, they're probably going to start doing covalent bonds, or here and here. Nearby elements form covalent compounds. Covalent compounds form when elements have roughly equal tendency to accept electrons. Elements that are nonmetals and therefore close to together on the periodic table tend to form covalent compounds with one another because they have approximately equal tendency to accept electrons. Compounds involving carbon, silicon, nitrogen, and oxygen are often covalent. Okay, so if carbon is often covalent, then pretty much silicone and all these down here are going to be covalent. And if nitrogen is, then pretty much phosphorus and arsenic and all these guys down here are going to be covalent. And if oxygen's usually covalent, then sulfur, selenium, all these guys down here are going to often be covalent as well. All right, because they are in a family, and families act alike. Okay. Wow, do we need to take notes there? Yeah, I'm going to stop. Why don't you stop it and take what notes you think you need to make, and I'm going to look ahead. Okay. So let's look at the solvent, predicting ionic and covalent bonds. Potassium combines with bromine to make the salt potassium bromide. Is this likely to become an ionic or covalent bond? Alright, so we've got potassium over here, and we've got bromine over here. And they are really far apart, so they are going to make that wonderful ionic bond. Okay. Let's look at the next one. Is silica, SiO2, where is Si? Here's Si, and here's O. They are really close together, so chances are they are going to make a covalent bond. Okay? And then calcium fluoride, calcium, and we're looking for fluoride. They are really far apart on this chart here, so chances are they're going to be ionic. Okay? Still learning about that periodic table, aren't we? Alright, so you are responsible now for doing your check understanding, and that goes on page 1. I wish my eyesight was better. Check understanding. It goes on page 118 in your student journal. You're going to go ahead and do that. You need to do 1 through 7, and when you're done with it, we're going to go over it in class probably on Wednesday, I guess. But you got to remind me. So that's it. All right. Happy homeworking. Bye-bye.